Hello everyone. So today I guess I'm hoping that today will be the last video for 14.7. I have two examples I want to show you, but as you noticed from my last video, it went a little bit over 30 minutes because the example was taking a little longer than expected, so to speak. So I'm hoping that I can push both of these into this one video, and the last two examples I want to show you into this one video, and that would be it. That will be everything that I want to show you in differential equations. So I guess we should get started. So our last example show us that we can actually try to form a power series of a solution of a differential equation that we don't know how to solve yet. And that will be this one right here, y double prime minus 2x y prime plus y equal to 0. Even though it's a homogeneous differential equation, because of the x, we really have no idea how to deal with this, because all the examples that we have done so far deal with a differential equation of usually first order. Then we can use exponential multiplier method or integrating factor method. And if it's higher order, we usually deal with just constant coefficient differential equation. So that's this is really something new that we haven't done. And as we've gone through the example, we actually found this really massive power series solution where it has c sub 0 and c sub 1x, and they have these two powerful summation, one for the even power term and one for the odd power terms. And it doesn't really have a nice pattern to it either. The top has to have some kind of weird looking multiplication throughout a arithmetic sequence. But nevertheless, we have a solution that we can actually use to generate as many terms as we need to approximate whatever solution, whatever x value we want to get our y value. So now what is the next step? Well, the next step would be to talk about what if we have a non-homogeneous solution. Can we use this method to solve for it? Well, yes, you can. The only problem is that it will be a lot harder to do if we are dealing with a non-homogeneous differential equation where the differential equation is actually equal to a function that has its own power series, like e to the x sine x or cosine x, because then it will require you to kind of pay up the coefficient and find some way to actually correspond them together. So that is something that I do not intend to ask you, and so I'm not going to give you an example of those, since I'm not going to ask you to do those, but I will ask you to do non-homogeneous differential equation of this type where the differential equation is actually equal to some kind of polynomial on the other side, and want to show you how to deal with that. So let's show you these two examples. So hopefully it will help, will make sense. Oops. Okay, our first example is this one. Very straightforward one, just to illustrate my point. Suppose I have y double prime plus y equal to x squared. And I'm going to go and ask you to solve this differential equation using a power series solution. Now, if you think about it, we already know this part of the solution that we need. Why? Remember, this equation, the solution, we call the solution to a non-homogeneous differential equation is always in this form. Y equal to y sub h plus y sub p. And we actually already know y sub h because we actually did that already. So I'm not going to redo the same thing. Let's just look it up. It's right here. Y double prime plus y equal to 0. We find out that our power series solution should come out to be c sub 0 cosine x plus c sub 1 sine x. So I'm going to just use that. So we already know y sub h is c sub 0 cosine x plus c sub 1 sine x. So that's half of the solution that we need. So what I now need to do is actually just to simply try to figure out what is y sub p. So that's what I want to show you with this example. So how do we actually find out what y sub p is? Well, it's actually doing the exact same thing. So to find y sub p, we will start the process in the exact same way. Meaning what? Meaning we're going to let y sub p equal to summation k from 0 to infinity c sub k x to the k. And therefore y sub p prime would equal to summation k equal to 1 to infinity c sub k times k times, well, maybe I don't need a parentheses, c sub k times x to the k minus 1. And normally we reindex it, but in this case, it really doesn't matter what y prime is, so I'm not going to worry about it. Y double prime, however, I do want to know, put that up here on the equation. So y sub p double prime would be summation k from 2 to infinity c sub k times k times k minus 1 x to k minus 2. So this one we do want to reindex because I need it to be x to k. So we're going to start at 0 and I'm just going to add 2 to all my terms. So now everything here is exactly the same. So now what I'm going to do is I'm going to form my differential equation. My differential equation is y double prime plus y equal to x. So therefore imply that is summation k from 0 to infinity c sub k plus 2 times k plus 2, k plus 1, x to k plus summation k from 0 to infinity c sub k x to the k is equal to x. Now that is crucial because of the following. So what we're going to do is combine these two summation together to form one summation. Now notice that here is where it's different. See, before, when we have the homogeneous differential equation, I would simply just say that all the coefficients just become 0. Because equal to 0 is a homogeneous differential equation. But now what we have is not a homogeneous differential equation. So how does that change the problem? Change the problem this way. So instead of looking at the x, what I'm going to do is I'm going to say, well, how about we look at this? Is 0, x is 0, plus 1 x to the first, plus 0x squared, plus 0x to the third, plus dot dot dot. So meaning that every coefficient a sub n is 0, but except one of them, a sub 1, which is the coefficient for x to the first power, is actually 1. Now, how does that change the whole dynamic of the equation? Well, let's write them out and see. So in here, we're going to deal with, once again, just like what we did before, we're going to deal with constant term. That will be, in this case, k equal to 0, because that will give me x to the 0 power. And therefore, on the left-hand side, I will have c sub 2 times 2 times 1 plus c sub 0. And that should equal to the coefficient for the constant term on the other side, which is the x to 0 term, which is 0. The next one is the x term, which is when k equal to 1. That will give me c sub 3 times 2 plus c sub 1. But this one is not 0 because there is actually a coefficient on the other side of the equation. This one actually equal to, oh, I'm sorry. I actually want to, it's not too exciting if I do, oh, it's not to say x squared, so I'm going to put x squared. So I actually have to fix this right here. So this one would be 0 also, but this coefficient is 1. And I need to put a square right there. Oh, there you go. Now it all works out. Let me just double check. Yeah, I did do x squared. So this one will also be 0. Now, the x squared term is the one that's exciting. If I k equal to 2, that will be c sub 4, 4 times 3, plus c sub 2, and that is actually equal to 1. The rest of them will all be 0, and I'm going to write out just a few more just to illustrate my point, and also will help me see some kind of pattern involved. So the next one will be this one. Oops, it's 5. 5 times 4 plus c sub 3. This one is 0. X to the fourth term is k equal to 4. So c sub 6, 6 times 5 plus c sub 4 equal to 0. And let's do one more, x to the fifth term, which is k equal to 5. And that would be c sub 7. 7 times 6 plus c sub 5. That also equal to 0. And then this continue on forever. So now how do I deal with this? Before everything equal to 0, I can nicely form a recursive formula, and then I can use it to basically generate all the coefficient. But here, I now don't have everything equal to 0. I actually have one h1 that does not equal to 0. So this kind of screw up everything. Well, it's true. It does. It's kind of screw up the recursive formula. But lucky for us is the following. We are looking for what we call a particular solution, meaning there could be potentially a lot of different solutions that would fit this differential equation, and all I need is to find one of them. And of course, I would say all I need is to find the easiest one of them. Okay? So, how do I find the easiest one? Well, notice that every equation is equal to 0 except this one equation which is equal to 1. So let's work on this unique equation right here. And when we try to satisfy this particular equation that's equal to 1, I can do one of three things. And we're going to try to pick the easiest out of these three things we can do. So it really depends, but here are one of the three things we can do. Number one, we can let c sub 2 equal to 0 and c sub 4 equal to, 112. So that would allow me to satisfy this equation, because it would be 112 times 4 times 3 plus 0, which is 1. Another one is to reverse the process and say, let's say c sub 2 equal to 1 and c sub 4 equal to 0. Okay? And finally, what I could do is just have c sub 2 and c sub 4 be any pair of number that would satisfy this equation, make equal to 1. So in this case, I could say c sub 2 just equal to 1 minus 12 c sub 4. And therefore now allow me to literally use any pair of c sub 2 and c sub 4. So which one of these three options is the best one? So the first one I'm going to cross out is this one. But that would definitely, create a lot of different scenario with c sub 2 and c sub 4 both being in numbers. Okay. So now what happened to the other two scenario? Well, then what we have to do is look at, if I choose c sub 4 to be a number versus choosing c sub 2 to be a number while there is 0, which one would have a longer or more lasting impact in our solution? And we want to do one that does not have a lasting impact. So here, if I look at this correctly, if I do make c sub 4 to be 112, then notice what happened is the following. If I make c sub 4 to be 112, it will then affect this c sub 4 right here, which will imply that I will now have to deal with c sub 6. And c sub 6 will most likely deal with well, actually, let me write out one more equation, then you can see. So therefore, if I do choose c sub 4 to be 112, that would force c sub 6 to be some value, so it can balance out c sub 4 to give you 0. And if that would make c sub 6 to be something non-zero. And if c sub 6 is non-zero, then it will have an impact on c sub 8. So therefore, by choosing C sub 4 to be 0, what the impact is the following. If we choose C sub 4 to be equal to 112, which is not 0, then it will impact, it will change C sub 6 to be non-zero, which C sub 6 non-zero will change, it will imply, I guess, that C sub 8 cannot be 0. And so therefore, this process would go on and on forever. And that would imply that we will need to now find out what C sub 6 is. And then when we have C sub 6, we'll have to find C sub 8. And once we have C sub 8, we have to find the next one, which is likely C sub 10, so on and so forth and so forth. That seemed like a long process. Why would we do it the other way? What happens if I choose C sub 2 to be a number, but let C sub 4 be 0? If C sub 4 is 0, C sub 6 will be 0, and C sub 8 will be 0, and so on and so forth. But what kind of impact for making C sub 2 not 0 would do? Well, let's see. If C sub 2 is not 0, it would forces the first equation that involves C sub 2 and C sub 0 to have some kind of way to balance to be 0. But that would be it. Notice that C sub 2 happened to contain equation before it, but there's only a finite number of equations before C sub 2. But if I deal with C sub 4 not being 0, then there are infinite number of equations after the equation for x squared that I have to now deal with because of the fact that it's not 0. So therefore, in this scenario, the easiest approach is to do the following. If we choose C sub 4 to equal to 0, then it will imply C sub 6 to be 0, C sub 8 to be 0, and so on and so forth. And if they're all 0, then I don't have to worry about them. That's the important part. So in this case, the best option that we're going to do is this one. So now I can try to figure out what would be the correct solution to this, what would be a particular solution to this differential equation. So first I'm going to do is the following. I'm going to go ahead and do this. I'm going to go ahead and let C1, which is equal to C sub 3, which is equal to C sub 5, and they all equal to 0. Notice that if C1 and C3 both equal to 0, it will automatically satisfy the second equation. And if C5 equal to 0 also, C sub 5 plus C sub 3, that would also equal to 0. And so on and so forth. Now, normally that will form a trivial solution, but remember, as long as I don't make all the coefficients equal to 0, my solution is not trivial. So we're okay. Next, I'm also going to let C sub 4 equal to C sub 6 equal to C sub 8, and these all equal to 0 also. And notice that would satisfy every single equation from x to the 4th down to x to the 6th down to 8 to the 8th, and so on and so forth. So the first statement right here, it will satisfy all the equations that involve x, x to the 3rd, x to the 5th, so on and so forth. And this will satisfy every equation that's our x to the 4th, x to the 6th, x to the 8th, so on and so forth. So now all I have to do is just worry about what's left that I have to yet to satisfy. So if you're keen on looking at it, you notice that we need to satisfy two things. X squared is missing from both of these statements, and also the constant term C sub 0. But we're okay. In here, what we're going to do is we'll let C sub 2 equal to 1. So this would satisfy the equation for the x squared equation. Because that would be 0 times 4 times 3 plus 1, which is equal to 1. Okay? And so now I just have to figure out what C sub 0 is. So if C sub 1, C sub 2 is 1, then C sub 0 would have to be the following, because it has to satisfy the equation for the constant term. So therefore, it would imply that 1 times 2 times 1 plus C sub 0 equal to 0. Imply that C sub 0 equal to -2, and that would now satisfy the constant term. So therefore, meaning that our particular solution, y sub p, should equal to z sub 0 times x is 0, plus c sub 1, which is 0 x to the first, c sub 2, which is 1, c sub 3, which is 0, c sub 4, which is 0, c sub 5, which is 0, c sub 6, which is 0, and so on and so forth. So therefore, if you think about it, all the 0 coefficients just go away, and therefore just leave you with this. That is my y sub p. And therefore, our solution, y, is equal to c sub 0 cosine x plus c sub 1 sine x plus x squared minus 2. Oh, actually, you know what? I'm going to write it as minus 2 plus x squared, since that's what I write my particular solution. There you go. Well, with this video already 21 minutes, and I really don't want to get into my next example, I am going to have to make another video. So I guess I'll stop right here and give you a short video. And our next video will be the last example that I want to show you, and then that will be it. Alright, I'll talk to you guys again in the next video. Bye-bye.